Hello guys, we're gonna start our third lecture on chapter 12 today. So in this lecture, I'm gonna talk about vector analogy, or I'm gonna talk about representing any arbitrary vector in space using three mutually orthogonal vectors. So you know that if we have any vector in space, we can represent this vector in terms of I, J, and K component, which is, they are along X, Y, and Z axis. For example, let's assume I have one arbitrary vector like U. So I can say that U is equal to, for example, X component, so I call it U1I plus U2J plus U3K. So U1 is X component of the vector, U2 is Y component, and U3 is Z component of vector U. But you know, in general, if we assume V1, V2, and V3 are three mutually orthogonal non-zero vectors in space, any 3D vector can be written as a linear combination of these three vectors. For example, vector U can be written as C1 times V1 plus C2 times V2 plus C3 times V3. In this case, C1 and C2 and C3, they are all constant. So we can easily find C1, C2, and C3 in this case. So if you want to find these three unknown coefficients, in order to, for example, in order to find C1, what we have to do, we have to find inner product of vector U and V1. So if I find inner product of vector U and V1, so it's equal to, we said that inner product for the vectors is the same as dot product. So U1 is C1 V1 plus C2 V2 plus C3 V3 dot vector V1. So it's based on properties of inner product. So we have C1 V1 dot V1 plus C2 V2 dot V1 plus C3 V3 dot V1. So it's equal to, in fact, inner product of vector U and V1, it's equal to V1 dot V1. So we know that it's, so we have C1, V1 dot V1 is magnitude of V1 squared plus C2 times V2 dot V1. So we know that V2 is perpendicular to V1. Based on definition, we have three mutually orthogonal vectors. As a result, V1 and V2, they are orthogonal. So we know that inner product of orthogonal functions is equal to 0. As a result, V2 times V1 is equal to 0. So we have the same for V3 dot V1. So V3 and V1, they are orthogonal. As a result, the inner product is equal to 0. So here we can say that C1, it's equal to inner product of U and V1 divided by magnitude of V1 squared. So we can do the same procedure for C2 and C3. So C2 is going to be equal to inner product of U and V2 divided by magnitude of V2 squared. And C3 is equal to inner product of u and v3 divided by magnitude of v3 squared. So we could find C1, C2, and C3. So at the beginning we said u is equal to C1 V1 plus C2 V2 plus C3 V3. So C1 V1 plus C2 V2 plus C3 V3. So it's equal to summation of, if I want to write it in the compact form, Cn Vn n from 1 to 3. It's equal to, so here we found Cn. Cn is inner product of vector u and Vn divided by magnitude of Vn squared times Vn. So we could write vector u in terms of three mutually orthogonal vectors v1, v2, and v3. So now I'm going to solve one example to see how this equation works. So write u equal to 2i in terms of three mutually orthogonal function vectors v1, which is equal to I plus 2j plus 3k, v2 is 2i minus 4j plus 2k, and v3, which is I plus 0.25j minus 0.5k. So in order to find vector u in terms of v1, v2, v3, so we have to find c1 times v1 plus c2 v2 plus c3 v3. And we said if you want to find c1 is equal to inner product of vector u and v1 divided by magnitude of v1 squared. So what's magnitude of v1? Magnitude of v1 squared, it's equal to coefficient of I, which is 1 squared, plus coefficient of j, which is 2, so it's 2 squared, plus coefficient of 3 squared, so it's going to be 3 squared. So as a result, it's equal to 1 plus 4 plus 9, it's 14. What's inner product of u and v1? Inner product of u and v1, so in fact is inner product of 2i and I plus 2j plus 3k. So we have I coefficient of I times coefficient of I here, so we have 2 times 1 is 2 plus, so here we don't have any coefficient for j and k, as a result it's equal to 2. So it means that c1 it's equal to 2 divided by 14. So if you want to find C2 is equal to inner product of u and v2 divided by magnitude of v2 squared. So it's equal to inner product of u and v2, it's equal to inner product of 2i and 2i plus minus 4j plus 2k. So it's equal to 4, and magnitude of v2 squared is equal to 2 squared plus minus 4 squared plus 2 squared. So it's going to be 4 plus 16, it's going to be 24. As a result, C2 is equal to 4 divided by 24. And now we have to find C3. C3 is inner product of U and V3 divided by magnitude of V3 squared. So we can find inner product of U and V3. It's equal to inner product of 2I and I plus 0.25J minus 0.5K. As a result, the inner product of U and V3 is equal to 2. Now I have to find magnitude of V3 squared, so it's equal to 1 squared plus 0.25 squared plus minus 0.5 squared, so it's equal to 1.3125. As a result, C3 is equal to 2 divided by 1.3125. So we could find C1, C2, and C3. As a result, I can say that I can represent U in terms of 3 perpendicular or 3 orthogonal vectors V1, V2, and V3. So in this case, C1 is 2 over 14 times V1 plus 4 over 24 times V2 plus 2 over 1.3125 V3. So we could represent this vector in terms of 3 orthogonal vectors V1, V2, and V3.